Share my screen. So hi everyone, welcome to the Multimodal Weekly webinar series hosted by the team at Tu-Anh Labs. So we've been running this special webinar series every week over the past year and a half or so, every Friday. And we focus. Here's some of the topics. Here's some of the topics that we tend to cover on a weekly basis. New research in multimodal AI and foundation models, innovative application of multimodal in different verticals. Since at Tu-Anh Labs, we focus a bit more on video. Sometimes there's people talking about the application and projects they build with, video AI and multimodal AI. And then finally, we sometimes have team members giving tutorial guides on using our platform and API. So in some of the recent session, we have a wide ranging of, speaker persona from, say startup people, working on technology to enable multimodal in the real world, to one of our partners talking about application of multimodal AI in different verticals, to researchers working in like evaluation of language model and multimodal for audio processing, to the application of multimodal in like media and video production and search. For today's session, I got a chance to get connected with the team at Meta AI, including Benjamin Muller, Bokai Yu, and Tu-Anh Nguyen. They been working on this paper called SpiRit-LM, which is a foundation multimodal language model that mixes text and speech. And so I think I'm super excited work that showcase, how we can design a system that can like take the best of both of these modalities and like, achieve a certain specific outcome. So super excited to hear them walk through, the motivation, the technical advancement, as well as some of the potential application of this research work. So just a quick logistic note for the attendees: feel free to send your question on Zoom chat, and I can surface them to the presenters as they go through their presentation. And we also have I think the presentation is going to be roughly between like 35-40 minutes in total, and then we'll have a Q&A session between like 10 and 15 minutes after the speaker finish. Yeah, so with that, I will stop sharing my screen, and I let Ben, if you want to go ahead and start with your presentation.
Awesome. Thank you, James. Can you see my screen?
Yep, I can see it.
Perfect. Okay. Hi, everyone. Thank you all for being here. Thank you, James, for the invite. So yeah, I'm Ben. I'm a researcher at Meta, based in New York. And with Tu-Anh and Bokai, we're going to present you SpiRit-LM, an interleaved spoken and written language model. So yeah, the talk should be about 35 minutes. If anything is unclear during the talk, like feel free to interrupt us, and we'll answer like questions. And we'll also leave time at the end for like discussions. So this work was done at the end of last year at Meta with a very large team of very great collaborators that you can see on this slide. We've released it on archive, so there are much more details in the paper. So I invite you to go there if you want to dive more. Okay, so let's start with some motivation of this work. So we've all been aware and probably using large language models like ChatGPT or Gemini or Meta AI. And it's pretty clear that these models are very, very powerful linguistic interface. Like we use them to correct our code. We use them to plan trips, to get help with like creative writing, or even to access knowledge. But what's clear also is that their mainstream usage remains very limited to the text modality. Like there has been a few interfaces that are popping up on the speech side, but most of these interfaces are based on an ASR system, which basically transcribe your speech into text. And then this text is basically fed to the same language models we use in the written form. So the core motivation of these projects is to build a foundation model for expressive spoken language modeling. Like, so why would we want to do that? Like, so first, the speech interface allows a much wider number of use cases than text only. It would open up like screenless usages, for instance, not having to type every time we need these systems. And the second, which is very interesting from a modeling point of view, is that if we're able to model expressive spoken language, it means that we can capture what we call like paralinguistic context. So it's basically the pitch of the voice, the tone, the volume, the energy of the user speech. Like, and through this paralinguistic context, this means that we can basically better understand the user intentions. And if we're able to communicate and generate speech in the same expressive manner, it means we can also communicate with users in a much more natural way. Like, so there is a lot of things that would be unlocked with expressive spoken language modeling. So why is it a challenge to achieve this? Like ChatGPT was released almost 1 year and a half, 2 years ago, but still we don't have yet like the very powerful like speech interface. Like, so the reason is that speech language modeling is hard, like, and it's way harder than doing text language modeling. There are a few reasons why. Like, one very intuitive way to understand why is that they are, for each written word, there are basically an infinite number of ways to speak it. Like, of course, it depends on the speaker themselves, but even for a single speaker, it depends on the context, like which would impact the tone, the volume, the style of the voice, or the energy. Like, which means from a machine learning perspective that the data is much more sparse, like, and it's much harder to learn from spoken data than from written data. The second reason is that voice is a natural biometric data, like we can identify speakers thanks to their voice, and which means that we cannot get any data we want in the spoken domain. Like, we need to there are clear rules and clear constraints about the data we're allowed to do, and we also need consents in many settings to being able to train or encode data that comes from specific users. Like, the third reason why speech language modeling is hard is that the sequence length that comes when we discretize and tokenize the input speech, the sequence length is typically much longer than what we do with text. Like, the rough like rules of thumb is that one text tokens, which is typically one text BPE token, is roughly equivalent to 7.5 speech units. Like, if we take a unit to be 40 milliseconds of speech, like, this means that for the same semantic content, we have way longer sequence lengths to model. And finally, the final reason why speech language modeling is hard and harder than text is that we don't have the same amount of data and of speech data resources compared to text. Like, if we take what was used for Llama 3, which is roughly about 15 trillion tokens of text, so 15,000 billion tokens, what we are able to achieve right now in speech is almost 3 orders of magnitude under that. Like, for SpiRit-LM, we were only able to collect about 4 billion tokens of speech data, like, which shows that if we take the scaling laws as this law that tells us that we need to scale model size and data set size to really achieve very good generation capabilities, this means that we are basically very far away, and we need to find better modeling approach in order to achieve the same kind of experience in the speech modality. So in this talk, we'll introduce you SpiRit-LM. So Tu-Anh will present the architecture and the training recipe, and then we'll dive in the evaluation of the system. We had to introduce like new benchmark also for the system in order to measure the expressivity of the system. And finally, we'll conclude with some ablation experiments in order to understand what are the key ingredients in the SpiRit-LM modeling. So I will leave Tu-Anh move forward with the talk.
Yeah,
I think
I think you're muted, so you can unmute.
Sorry. So, hi everyone, I'm Tu-Anh. So, I'm happy to be here today, and now go with the architecture of the model. So, the SpiRit-LM model is basically just a combination of the text language model and speech language model. So, as you can see here, a classic text language model consists of first is text tokenizer. Normally, it's like sentence piece or PD tokenizer. The text are then encoded to text tokens and then are fed to the language model to produce new token, and then which are decoded back to text with the decoder. So similar, based on this idea, there has been several work on speech language models. So notably the GSLM family or TWIST or audio LM. So they first tokenize the raw audio into sequences of a speech token or a speech unit with half of the speech encoder. Then the speech unit will be fed into the speech language model, and finally the generated speech unit will be decoded back to speech with the help of a speech decoder. Here it is very similar to what you see in the text-to-speech models. And so in this work, we just compare the best of both worlds. So we want to have the model that can take in input both
speech.
Yeah. No. Okay. We have different encoders for text and speech to obtain text and speech token in the input. We put that to model, and the model can also generate text and speech with the help of the decoders. So let's look into more details of how we treat the unit. So the next slide. So here we assume that in this we are in the situation where we have a small data set of the aligned speech and text data set at the word level. So for example, here the cat sat on the mat, we have both the speech and the text. Then we will, for each word, we will mask randomly one modality, so either speech or speech text. In this case, for example, we choose the speech, the cat sat on in text, and the mat in speech. We then use the different speech and text encoder to encode them into speech and text tokens correspondingly. And then we'll put interleave this token and prepend each modality with the speech modality token or text modality token and put that to training. And during inference, we can use this speech modality token or text modality token to guide the model to generate the modality that we want. So let's talk about the speech tokenizer. So we have 3 types of token that we use in this work with different temporal size. So the first one is the semantic token, which are the same kind of token that has been used in previous work like GSLM. So in this work, we use Hubert. So Hubert is a self-supervised speech model that can capture acoustic information from the speech. So basically, each token can contain some phonetic-like information from the speech. And then we have a k-mean clustering to discretize this feature. The second type token is the pitch token. So we want to capture the intonation in the speech. We extract the fundamental frequency or the F0 of the speech, and then we train a VQVE model to capture a long range of indentation, and then it will discretize them into units of 80 milliseconds. And finally, we will extract something called style token. So we have we extract something we call speech prof feature, which is from the Sono Expressive from the other work in Meta. And these features are supposed to capture the expressivity information in speech, such as happy or sad or even laughing. We extract the feature, and similarly to the semantic token, we do a k-mean clustering to tokenize the feature. These tokens are first deduplicated, so similar to previous work, and then interleaved from a single sequence of tokens so that we can feed that to the language model later. On the decoder side, we train and we use a hi-fi GAN vocoder. So we train the hi-fi GAN vocoder condition on the semantic token, the page token, and the style token to resynthesize the speech from this token. So for the training, we initialize the model from the Llama 2 7B model. We later show that this is actually beneficial for the cross-modality learning. And for the data set, we we want that our model is able to perform well, not only for in cross-modal dataset, but also in text only or speech only. So we have 1/3 of our dataset in speech only, 1/3 in text only, and 1/3 in with the interleaving dataset. For the interleaving dataset, we uniformly sample from 10 to 30 consecutive words in each modality to ensure that the model have a single variability of the dataset. We train the model for up to 200 billion tokens. We have two different versions of the model. So the first one is SpiRit-LM based, which only use the Hilbert token. So to be comparable with previous work, which only use semantic tokens. And we'll also have another version, SpiRit-LM Expressive, so which combine Hilbert style and pitch tokens to capture the expressivity in the speech. Yeah. And so here are some examples of our generation. So the model is actually able to generate not only in one. So given the speech input, the model can continue either in speech or in text with preserving the semantic content and vice versa. So we show some example on this website. Benjamin, can you? Sorry.
Let me play some examples. So yeah, we released a few generation on this website you can go play with. So for instance, if we prompt the model with the text modality, we can ask the model to generate a speech sequence. So for instance, here, the example of the prompt is the largest country in the world is, and we do next token prediction on the speech modality. And let me play the generation.
Russia, our country, has about 150 million inhabitants. The second in size is Canada. The fourth is China. And the fifth is Brazil. The smallest country in all the world is the Vatican City. The capital of the United States is Washington. The most important cities are New York.
So here you can see that there is a clear cross-modal consistency, and the model has good knowledge also of the world in the speech modality, right? Because it was able to basically continue this prompt like correctly and found that, yeah, the largest country in the world is Russia. So this was the SpiRit-LM base. As you can see, there is no expressivity in the speech generated. Now we can listen to an example of the expressive model. So here we're prompting the model with input speech, and we're going to request the model to generate speech. So here's the prompt.
No, I think you're thinking about Days of Thunder, which is a Tom Cruise racing movie.
So the prompt is like happy sounding prompts, and then we ask the model to generate speech after this prompt.
Oh God, yeah, it was amazing. Was it the one where he was a monster in between rocks and stars?
So what you can hear is that, yeah, the generated speech is also expressive, and it is somehow following the expressivity of the prompt correctly, like, which is what we wanted to achieve. Like. So yeah, I invite you to go to this website. There's a lot of examples to kind of get a sense of the capability of the system. I'll go back to the slides.
Awesome. Yeah. Maybe we can leave a few minutes at this point for like just any question from the audience as we walk through the architecture and like the motivation. Yeah, from the audience, you guys have any question? Do you want to ask the team as they talk about some of the initial part of the model?
Can I ask a question, James?
Yeah, please.
Really awesome work, guys. It looks, I mean, the immediate thought after the last example is can it be used for voice cloning then? Because it looks like the response was following not just the general happiness level, but also the timbre of the voice was pretty much the same. Do you see that as a use case as well?
So yes, also as Benjamin say, who have this kind of privacy constraint in speech language model, and that's a very serious thing here at Meta. So the reason why the continuation here has very similar voice is that we condition the hi-fi GAN token with the same speaker. If you see at the speech tokenizer, we have three kinds of semantic, pitch, and expressivity. And actually, we showed the paper that we have some sort of removing all the speaker information in this token. So basically, the information of the speaker is very, so I can, and I don't say that it's zero, but it's very little content in the token. And you can control the output voice at the hi-fi GAN encoder. So at least at the moment, it's not a risk for us.
Thanks. And I guess just a follow-up question. So in the Russia example, there were some hallucinations, right? I think it said China is fourth, not third. Are these coming from like, basically, is it the text modality hallucination? Like, what is this? So how does this work here with the speech tokens? Like, do you have insight on how it hallucinates?
So yeah, maybe I can take this one. So yeah, when we generate here, it's so we're doing next token prediction. So it has all the limitations that a text language model would have, right? So yeah, hallucination is definitely like one of the limits of these systems. And something to keep in mind here is that we're only doing the pre-training stage, right? It's only a foundation model. We didn't do any post-training in the system, right? And when we play with like ChatGPT or other like text language models, there is very significant work done in the post-training stage to basically reduce this hallucination, teach the model to not answer when it doesn't know, and also, yeah, it kind of improved the factuality of the system. Like, so this work wasn't done with SpiRit-LM. Like, it's only next token prediction. So it's kind of expected that, yeah, in some cases it will be incorrect. And in some cases, maybe it will just hallucinate stuff because it only knows to do like a next token prediction, basically.
Thanks a lot.
Yep. I'm actually also have two questions. So if you can go back to the model architecture slide when you talk about the interleaving part. Yeah, so this part here, can you, maybe I missed this part, but can you emphasize that part again, like the interleave between speech and text token and then the role of the BP token? Yeah, can you explain what it does and like how do you mix speech and text tokens together?
So as I say, so here, like, so in this case, we assume that we have this kind of aligned speech and text data set. So we have for each word, either speech modality or text modality. So when we go interleave, is mean that we keep the same context. So here the get set on the mat, but the modality of each word can be variable. So it can be either in speech or either in text. So if you see here, the first, for instance, the first three speech, the three blue square here represent the tokens of the speech segment, the cat, and the next two red square represent the text sat on, and the same thing for the last blue square. And so that means that's what's meant by interleaving. We also have add the addition speech or text so modality token before each of the modality to help the model to identify the correct modality, and it also happens at the inference time to control the modality of the output.
Maybe one other detail is that we're starting with Llama 2. So basically these tokens, they're fed to the Llama 2 pre-trained model. So we're basically expanding the vocabulary of Llama 2 to support these new speech tokens. Like the BP, we reuse the one that the model was pre-trained on. But for the speech tokens, we basically expand the vocabulary.
Got it. And you also mentioned like because you initialize, the model based on Llama 2 7B is already pretty powerful, right? In terms of multimodal capabilities. Is that because like Llama 2 is already a very strong base model?
So we have more results in the ablation actually, where we show the value of initializing with Llama 2. Like, but yeah, I mean Llama 2 is basically just a very good text language models. So the idea, the intuition is that we want to transfer some of this linguistic knowledge in the text modality to the speech modalities, right? To kind of address the challenges that I listed in the beginning, which is we don't have as much speech data, right? So we can't expect a speech model trained from scratch to be on the same level as Llama 2. Like, so the idea is to start with Llama 2 and try to transfer like these kind of linguistic capabilities.
Great. Yeah, I think that's all I have. We can move to the evaluation part.
So okay, so for the evaluation, we built the model on some zero-shot evaluation matrix on text and speech. We then also try the cross-modal few-shot evaluation matrix, and finally we introduce the so-called STSP matrix, which just evaluate the capability of generating expressive speech and text of the model. Yeah, so the first part is the zero-shot evaluation matrix, so very similar to this kind of same metric for TextLM. So we prompt the model with two different sequences. One is correct and another is incorrect. And we evaluate if the model assigns higher priority to the correct sequence. And in this work, we use 4 different metrics, which actually prompt the model at 4 different linguistic levels. So the first one is Googie, which focused on the lexical level. So normally this for the text language model is very easy because you have this kind of text tokenizer, which basically have the model to identify if it's the correct word or not. But for speech, it's very difficult, as Benjamin mentioned, because you don't have this kind of word tokenizer for speech. We have another metric at the syntax level, so clean. And here we have this kind of two sentences. One is grammatically correct and another is incorrect. We have two additional metric called topic story clause and story clause, which is at a broader level. So this the sequences here has the same context. So here, for example, Lisa had good notes. And for the topic story clause, the incorrect one is unrelated to the correct one. So she is happy and Bob plays football. And for topic story clause is a little bit harder. So both sentences are in the same domain, but one is more like correct. So she is happy because she had a good note, and she's happy that she had good notes. So here we show the model performance on the texture metric. In red, we have the Llama 2 model, and in purple, we have the SpiRit model. So we see that both models are performing similarly on texture metric. Given that we continue to train to extend the Llama model to the speech modality. Yeah, so that's for the text. For the speech metric, here we compare the model with the previous work on the previous SpiRit-LM model. And we see that the SpiRit-LM is pretty comparable with previous work, and it even achieved a SOTA on topic story clause and story clause, while like being smaller than the twist 30 billion model. And however, compared with the cascaded baseline, so we also perform the top line where we use the Whisper model followed by the Llama model, and actually this model is performing better than our model in all the cases. This is not very surprising given that the Whisper model itself has a lot of aligned speech and text data set, and which was trained only on the speech recognition task, and which we only use a small subset of aligned data set, and we train with the language modeling task. And finally, we found that it's interesting to see that actually SpiRit-LM can perform cross-modal tasks. So here we use the topic story clause and story clause task. We'll have this kind of cross-modal task in the sense that we have the context in speech and or text, and the continuation is in another modality. So we see that the model is performing well, so better than chance on all the tasks. But if we see closely, generally the direction from speech to text is better than from text to speech. We then try the method of few-shot prompting, so cross-modal few-shot prompting for SpiRit-LM, and it actually turns out that the model is able to perform that, even if in the training we've not forced the model to do such a thing. So here we show the model performance on the three tasks. So first is intent classification, which is in purple. And we have the speech recognition in red and text-to-speech in yellow. We see that given more example to the model is generally have the model to achieve a better performance. So which is very similar to what we observe for the GPT. So for LLM actually models. And it's also interesting to note here that as similar to what we observed before, the performance of for the speech to text size or ASR or intent classification here is generally better than the other side, so from text to speech. Yeah. So now Benjamin, maybe we can continue with
Yeah.
SpeechLM.
So far we've seen the performance of SpiRit-LM on semantic metrics, like without really measuring the expressivity of the system. So to actually do that and measure how expressive is SpiRit-LM, if the model is able to understand also the expressivity of the input, we designed a new benchmark that we call like text speech sentiment preservation benchmark, or STSP. And the idea of this benchmark is basically to measure how good is the model at generating continuation in speech or in text that follows the same sentiments as the prompt, basically. And to dive a bit more, basically, there is strong correlates in expressivity between the semantic, so the words themselves, and the phonetics, like how the words are being spoken. Like, and what we're trying to measure here is if the model is able to have this knowledge, basically, of spoken language. So the way the benchmark works is we have prompts. For instance, in the speech modality, each prompt is part of one of the 3 sentiments. It could be a happy voice, a neutral voice, or a sad voice. And based on these prompts, we're going to generate, for instance, a speech continuation. Like. And what we want to measure is, does the generated speech follow the prompt sentiment? Like, so for instance, if the prompt is happy, we expect the generation to be happy as well. Like. So we do that in basically all the possible direction. So we do speech to speech. We also do speech to text. So given a happy speech prompt, we expect the model to generate in the text modality a happy written sentence. And we do that in the other way, given text prompts. So it could be a happy text, like the story is so fun, or sad text, like the story is so depressing. And we expect the model to generate a happy generation in the speech modality or in the text modality. We evaluate the sentiment of the generation using speech and text sentiment classifier. So we do that automatically, so it's definitely not a perfect metric. To do it more accurately, we would have to do like human annotations, which we couldn't really do in this project. But that's basically give us a good proxy of the sentiment of the generation. So we basically experimented with SpiRit-LM. We used the base model, the expressive model, and we compared to our cascaded top line, which is made of an ASR system, Llama 2, and a TTS system. And what we found is that SpiRit-LM expressive beats very significantly the cascaded top line. Like basically, if you only use ASR and Llama 2, you will not be able to perform this sentiment preservation benchmark. And the reason is that the sentiment of the speech prompt is lost when you do the ASR. But with SpiRit-LM expressive, the model, thanks to the style and the pitch tokens, we're able to capture that and achieve, for instance, 54% accuracy in the speech-to-speech direction, which shows that the model really captured the property that we were expecting about expressivity. So as a quick summary so far, so we basically introduced SpiRit-LM, which is a speech-text expressive language model based on Llama 2. It performs better than previous work on zero-shot tasks and cross-modal tasks. It can also learn tasks in the in-context few-shot learning setting, similarly to what was observed in the text large language models. And finally, it outperforms the cascaded top line on this new expressivity benchmark. What I'm going to present now is basically an ablation experiment to understand what are the essential elements of SpiRit-LM. Like, first, we want to understand, okay, we're able to do expressive modeling, but is there a cost in doing that? Like, Second, what is the value of initializing with Llama 2? Is there any value in doing that? And finally, we introduce this new interleaving scheme. Sorry about that. And we want to understand if there is any value in doing so. So here is the performance of SpiRit-LM on 4 benchmarks that captures different property of the model. So for text performance, we use MMLU, which is a popular text text benchmark. For speech performance, on the semantic side, we use story close. For the in-context learning capabilities, we use intent classifications. And finally, for the expressivity, we use the STSP benchmark. So here we're looking at the performance of SpiRit-LM base, which is in yellow, compared to the cascaded top line, which is made of ASR plus Llama 2. So the first question is, okay, what is the cost of modeling the expressive tokens into the model? So what we see is that the expressive tokens into the model allows us to perform way better than chance on the STSP benchmark. This is what I presented earlier. But what we observe also is that these new capacities for the model come with a cost, because we observe a small degradation on the semantic benchmarks. And this, we observe it for both speech and text. Second question is, okay, is the Llama 2 initialization useful? So for that, we've run the same SpiRit-LM training, but by initializing the system with a random neural network and not Llama 2. What we found here is that initializing with Llama 2 is very important. If we don't initialize with Llama 2, we degrade very drastically on the text benchmark, which is very expected, because Llama 2 is a very good text language model. But we also degrade very significantly on the speech benchmarks, for instance, on intent classifications. We degrade by almost 50 points, which shows how important is initializing with Llama 2. And finally, we want to know how important is the interleaved data training. So we run the same SpiRit-LM training, but we remove the interleaved data and we only train on speech-only data. So that's the bar plots in blue. And what we found again is that if we don't do interleaving data, we're not able to do any cross-modal tasks anymore. We forget all the text capacities. That's what we observe on the MMLU benchmark. Here, the blue bar is it's at random chance. And interestingly, we also degrade quite significantly on the speech benchmark themselves, which shows that interleaving helps the model transfer the pre-trained text knowledge to the speech modality. And to understand why, we basically looked into the representation of the model to understand why is this interleaving data impacting the model and how it is helping the transfer. So Tu-Anh had some very cool analysis on that. Go ahead, Tu-Anh.
Okay, sorry. So actually, we just so we just want to know what is the key behind the interleaving scheme. So we try to extract the representation of the model with the spoken and textual input of the same sentence, and we found interestingly that at the middle layer of the transformer, there some sort of alignment between the representation of the same in text, in both in text and in speech modality. So which suggests that the model is treating actually treating the content, the actual content of the both modality, and not treat them separately in two different subspace. As we can see here for the model without interleaving task, it has a very low similarity and is not observing this kind of alignment in the hidden layer of the transformer. So you can move to the next slide where there's some sort of animation of the alignment. So as you can see in the middle layer, there's some sort of alignment with the same word in the text modality and the speech modality. And it kind of tend to vanish in the last layer because there's some sort of network computation task. Yeah, so I think that's all from our side. So here we know that Interleaved dataset is and lemma 2 initialization is essential in SpiRit-LM. So yeah, I just some open question, and if you have any other question, feel free to.
Awesome. Great. Yeah, thanks guys for the in-depth presentation, and especially the very careful slide on ablation, right? I think showcase how it works, not just showcasing why it works, not just how it works. Yeah. Any question from the audience related to like the science behind and the building of SpiRit-LM?
I'll jump in again. Sorry. Again, really impressive, especially the breakthrough in the sort of not just semantic understanding, but the tone of the voice, the what's it called, the basically the sorry, blanks in my mind. But the question is, so sometimes it's really important to follow, say, some of these metrics. They follow the general sort of happiness level, but a lot of like the human speech is also in the accentuations, right? So like the way I'm saying a certain sentence, I can put a real big emphasis on a word. Like, is there a way even to measure? Because I feel like your approach has potential to also capture that from the from the input, from the prompt, and being able to follow that. Do you have any thoughts on like that? So like not just follow, say, the general kind of sentiment level of a sentence, but also have the intricacies within sentence of different accentuations or kind of different meanings that the speaker might put into the voice.
So actually, that's a very good point, and we do think of that before. The reason why we only capture the expressivity in the voice in the speech is that it's much more simpler for us to create the benchmark with just the three sentiments, and so yeah, and also because actually there's no previous work which concentrate on the sentiment or expressivity evolution of the generation from the SpiRit-LM, because it's not that common before, right? And we wanted to do something like which is not very detailed, but it is general enough to evaluate the capability of the current speech language model. So at least, so before GPT 4.0, we know that most speech-based model are text-to-speech, and it actually cannot handle this kind of expressivity even with the sentiment in the speech. And so that's why we don't want to go into very small detail like the emphasis, as you say. Not only that, maybe there are many other factors from the speech, like the laughter or the filler words or something like that. So that should all need to be evaluated and included in some evaluation metric someday, I believe. But because at the moment we don't have such a powerful model that we think that we might need this kind of a vibrant metric. But Yeah, I know if Benjamin or Bokai to have any thought on that.
Yeah, I think like maybe to add one thing is so we're definitely not evaluating what you mentioned, like because it's very hard for us to evaluate. But I think SpiRit-LM has definitely the key properties to capture it basically, because we're capturing the pitch separately from the semantics, and we also have the style encoded into the style token. So we basically have all the spectrum of speech data encoded to being able to model this. Like one challenge that we face during the project is to be able to capture it, you need the right architecture, but you also need the right data, right? And finding a lot of very diverse, very expressive data is like basically a very hard challenge to overcome. Like, but yeah, in terms of architecture, I think with SpiRit-LM we definitely have the key ingredients for that.
Yeah, thanks. I completely agree. I think this is one of the key kind of features that can come out of this approach. And then the second follow-up is like, okay, clearly there's some trade-offs between introducing the speech tokens, introducing the sentiment tokens, and then you lack some of the maybe text generation capabilities, right? So there's a little bit of a trade-off. Is there a way to kind of decompose that? Say, for example, I already have like a very, GPT-4 trained or some sort of a text model. Maybe I already fine-tuned something, right, for my use case. But now I just want to add that expressivity. I want to add the sentiment. Like, do you see a way to combine SpiRit-LM with other sort of pipelines to just kind of solve that problem, rather than trying to solve all problems at once with just like voice in, voice out?
So yeah, I mean, the approach we took with SpiRit-LM was we can definitely leverage and make use of very powerful text language models by doing basically continuous pre-training. That's what we've done with SpiRit-LM. But it's not really a plug and play approach, right? You have to train and to have the data, etc. If you look only at like very like strict pipeline approach where you're only plugging to like a text language models, it's very clear that, I mean, speech domains is just very different compared to text domains, right? So I think you have to go through an adaptation of the system to capture this expressivity, the different domains, the kind of domain gaps. Yeah, and then the question is, how do you represent this speech data, this speech modality? So here we chose like specific tokenizer. You could choose to do ASR, but kind of enriching ASR in like tricky ways. And on the TTS side, there is also a lot of ways to enrich, right? But I mean, one of the learnings of these past years in large language models and deep learning is that the more end-to-end you are, the more you're able to pre-train things end-to-end, the better properties will kind of emerge from your system, right? So that's also the intuition of if we're able to pre-train with the speech data natively into the model, like by doing early fusion, input and outputs of speech, like very interesting properties would emerge. And this expressivity is one of the first property. I think that's very interesting to see.
I see. Thanks a lot. I'll just, unless anyone wants to interrupt me, I'll throw the last one on the data set creation, right? So I didn't see a lot, maybe I missed it. I didn't see a lot of details on what is this data, right? What are these conversations, right? So, and then obviously there's a gap, a huge gap in size. Like, how do you see it being generated given the constraints, given the GDPR, whatever, like legislation on what data you can or cannot use? Like, how do you see basically getting more data for these kind of models?
Yeah, that's a very important and big question. So for SpiRit-LM, we basically relied on the text side on what was used for Llama 2. And on the speech side, we only use like open source data. So there is no like internal metadata used in the pipeline at all. and that would be basically impossible to do anyway. But yeah, the question is, how do you go, like how do you move forward? How do you get more data? Because as you've seen in the plots, we're still very far away from having text level scale data. And how do you get like very expressive data? So, I mean, yeah, without really revealing anything, yeah, there are definitely rumors and like discussions from like getting licensed data. So just paying for data, hiring people to get data. That's definitely one way to get, where you get consent of people who like give their voice. You can think of like, yeah, having like even actors playing in for you, like, but that's probably only will give you a very small amount of data, right? So on the very large scale pre-training data, I think the way, my intuition is what we basically did with SpiRit-LM, right? To try to transfer as much as possible from the text modality to the speech in order to kind of bridge this gap, like.
I see. Thank you very much.
Thanks.
Yeah. Yep. There's one question by Panay on the chat. We want to address that. So he asked, is there any testing on handling of accents, or it is a potential future work?
No, actually, we don't actually test the model capability to on accent, but one thing I could say we try to play something. We train the vocoder model on some French speaker, and the model is actually able to generate like the sentence with some French accent, but that's not but that's just from the vocoder part. So it's not coming from the actual 3 types of token that we introduced to the model itself. But that would be interesting to test it.
Great. Perfect. Yeah. I think we at time, but yeah, thanks guys for the great presentation. And I think some of the open question that you left at the last slide was also very interesting, right? From context length scaling to like, streaming pipeline. So I think those are very exciting. I could say like both research initiative and problem that I think the whole space is evolving. So yeah, I'm excited to see how Meta and the broader academic community will tackle that. Yeah, thanks everyone for joining. The recording of this session will be made available within the next probably like 3 or 4 hours or so. And yeah, I'll be sure to share that in the Discord community once it becomes available. Again, appreciate the speakers from Meta, both you guys calling from the East Coast and from Paris, for joining this session. Yeah, thanks for sharing, and hope you all have a great rest of your weekend.
Yeah, thank you so much, James.
Thanks.
Cheers, guys.
Bye.
Bye-bye.